Okay, so hello and welcome back. So in this video we want to talk about derivative, and we have basically talked about some situation where we talked about the derivative based on some example related to physics, and then we talked about we extensively talked about limits, and now we want to somewhat more formally basically define what the derivative of a function is. And basically, as you saw during that first situation that involved basically that involved that stone falling off a cliff. We had a stone over here, and there was a cliff over here, and then we had a piece of stone over here, and then this stone fell off the cliff, and then it was basically changing its position from here. If you imagine that the position here is 0, then it was, as time went on, it was basically changing its position from this point. Basically the position basically keeps changing as time goes by until it hits the ground at this point. So that is basically the situation of the stone, and we said that basically the position function of this stone with respect to time was s is equal to 4.9 times t squared, and then considering this relationship between s and t, of course you can, for example, write this relationship as, for example, y is equal to 4.9 x squared, for example. Then you can think of this as a general function, and of course the position, this position function with respect to time, or this y with respect to x, must be some function like this. Now we said that we basically what we said was that basically we took, for example, some point over here on the graph of the function. We called this, for example, t1, and then we started from any point on the graph of the function, call this, for example, t2, and then you can call this, for example, s2. You can call this, or basically y2, for example, in this situation. We write everything in terms of x and y. So suppose that, for example, this is the y-axis, and of course you see that y represents s and x represents t over here, so I already understand the example or what it represents. And this is x, this is y. Now if I call this, you can call this, for example, x1, you can call this x2. This is time. As time goes by, the position of the stone is changing from this 0 point goes, it keeps increasing and increasing and increasing, as you can see on the graph of this function. So now if I call this, for example, y2, and if I call this y1, we said that the average velocity of that stone from between x1 and x2 was basically the change in the position with respect to the change in the time. So we said that basically call it, for example, v is equal to basically y2 minus y1 over x2 minus x1, which you can write as delta y over delta x, the change in your vertical change over your horizontal change. And of course then what we did was that we took another point over here, and so we said that basically we now, in order to get a better approximation to to the instant velocity of the stone at x1, we pick this point because this point is closer to x1. So we call this, for example, x3 and y3, for example. So then again, we can say that v of 2, for example, calling this v1, v2 would be basically y3 minus y1 over x3 minus x1. You can again call this, this is not working. You can again call this basically delta y by delta x. And you keep doing the same thing, and you can see that over here, basically this delta y by delta x, this is your vertical change divided by your horizontal change. And that is basically the slope of this line. Again over here, this delta y by delta x, which refers to y3 minus y1 over x3 minus x1, is basically the slope of this line, which and you can just keep getting closer and closer to this point, to point x1. And so what happens here is that when you get very close to x1, when this point gets very close to x1, then you will essentially have some line over here that is tangent to the graph of the function. So you usually call these lines you call them the secant line. The secant line, and this line you call it the tangent line. And we say that in the limiting process, the secant line becomes the tangent line. And of course the slope of the tangent line, is the value of the instantaneous velocity of the object at x1. So basically what this whole thing means is that you have so this limiting process is basically this phenomenon happening over here. So we can say that your v1, for example, or basically in general v, is equal to the limit of basically delta y by delta x as delta x tends to 0, meaning that the difference between these 2 points becomes very infinitesimally small, basically. So now another way of talking about the same thing is that another way of talking about the same process is basically you can basically take this point as, for example, some point A, and I want to find the instantaneous velocity of the stone at point A. So what I can do is that I can take the position of the stone after some time after A, meaning that I can find f of basically a plus some h, meaning that h would be a very tiny distance in time, or a point in time interval after a. For example, let's say that this point over here, you can call it a plus h. So then f of a plus h would be this point over here, on the function. So this would be f of a plus h. Now imagine that, of course, you need to imagine that this distance is a very, very, very infinitesimally small distance, although it doesn't really matter, because we are going to take the limit of that, and then in the limiting process this distance becomes very, very small. So then I can basically calculate the value of the function at this point, and basically subtract from that the value of the function at this point, which is basically minus f of a, and then the value of the function over here is a plus h. Basically the time over here is a plus h, and subtract from that this time over here, which is a, negative a. And then if I take the limit of this, then this distance keeps getting very, very, very small, and with that this distance gets also very, very, very small, meaning that this point becomes practically the same point over here. The 2 points get very, very close to one another. And if I take the limit of this as this h, basically this distance over here is basically h, because if you calculate a plus h minus a, which is this distance over here, you will get h. So this distance over here is h. As h tends to 0, then this is going to be exactly the instantaneous velocity of this function at this point a, which is basically, you can cancel these two out, and then you can write this as the limit of f of a plus h minus f of a as over h as h tends to 0. And this is, of course, basically the derivative of this function. This is basically, this whole thing is the derivative of, this is the derivative of f of x at x is equal to a, which is of course the same thing as, which is of course in the context of the example of that stone, is the instantaneous velocity of the stone at t is equal to a, or at x is equal to a, something like that. So now this value, the limit of basically f of a plus h minus f of a over h as h tends to 0, has been called f prime. I mean, the notation for that is f prime of a, meaning that the derivative of the function f of x at point x is equal to a. And so basically, long story short, you can say that f prime of a is equal to the limit of f of a plus h minus f of a over, I think I wrote something wrong over here. No, it was absolutely right. Minus f of a over h, as h tends to 0. As h tends to 0, as h tends to 0, and that is the basically, of course, provided that the limit exists. And basically one important thing that we can note here is that f prime of a is the quantifies the change in f of x, at a with respect to x, because you could have actually more variables over here. You could have x, y, z, and probably many more variables. But what we are doing here, we were basically studying the change in the value of the function as x was changing, not any other, meaning that you could have many more variables basically changing at the same time in this whole scenario. But what we have zoomed in on basically x and y, and so based on the changes that we make in x, there will be some changes in y, and so the change in f of x, which is y, at this point a, with respect to x, meaning with respect to the changes that we make to the variable x, which is in this case time, okay, then that change basically is basically f prime of a, and basically that is the whole story. So to sum this last sentence up, or to just as some sort of reiteration, I would say that basically f prime of a is quantifies the change in f of x, meaning the change in the position of the quantifies the change in the position of that stone at this point a with respect to the changes that are happening in x, or with respect to the changes that are happening in time basically. And so you can say that basically f prime of a, which is the derivative of the function at point x is equal to a, is basically the rate of change of y with respect to x at x is equal to a. So that's basically what it is. Of course, in order to understand really what I said in this last sentence, you need to have understood the whole situation of the stone. Otherwise, well, there is no good way to understand these sentences that I just said. I just said that f prime of a is the rate of change, in f of x at x is equal to a with respect to x. Now what this is that, well, f prime of a, there is no problem with that, you understand it, because it's basically it's just the derivative, right? Now, this is the rate of change, meaning, well, the rate of change in f of x, in basically the position of that stone at x is equal to a, at exactly at the point x is equal to a, with respect to x, meaning based on the changes that are happening to time, as time is going by. Basically, what is the rate of change in the position of that stone? And to make it a little bit more abstract, you can say, well, this sentence, which is f prime of a is the rate of change in f of x at x is equal to a with respect to x. Okay, so that is that. Okay, so we are in this over here, 48, 49. Okay, so now let's do a couple of examples. Let's see how we can find the derivative of some functions at some points, for example. And that is, for example, you want to find the derivative of the derivative of, for example, f of x is equal to 3x at x is equal to 2. So we said that the f prime of a is equal to basically f of a plus h minus f of a over h. Of course, it has to be the limit of this as h tends to 0, and that is equal to the f prime of a. So now, based on this, f prime of x at x is equal to 2 would be f prime of basically 2, which is equal to the limit of f of basically 2 plus h minus f of 2 over basically h, as h tends to 0. And you need to calculate basically f of 2 plus h and f of 2 and put them over here. Now, f of 2 plus h is equal to 3 times 2 plus h, which is equal to 3 plus 6 plus 3h. And f of 2 is equal to 3 times 2, which is equal to 6. So I can write the f prime of 2 is equal to the limit of f of 2 plus h, which is equal to 6 plus 3h minus f of 2 minus 6 over h, as h tends to 0. You can cancel these two out, and then you can cancel the h's out. So then you have basically the limit of 3 as h tends to 0, which is equal to 3. Now, if you pay attention to basically what happened here, we got that the derivative of this function at x is equal to 2, the derivative of this function at x is equal to 2 as basically 3. So now what that means is that Now let's do one. Basically, let's calculate the limit of the same function, or the derivative of the same function at some other point. For example, let's go for let's say that, for example, your f of x is equal to 3x, the same function, and you want to find f prime of, for example, 10. The derivative of the same function at some other point, for example, not 2 but 10. So the way that you can do it is that you can write this as, again, we said that f prime of a is equal to the limit of f of a plus h minus f of a over h as h tends to 0. So again, you can write the f prime of 10 is equal to the limit of basically f of 10 plus h minus f of 10 over h as h tends to 0. Now again, f of 10 plus h is equal to, your function is 3x, so 3 times 10 plus h, which is equal to 30 plus 3h, and f of 10 is equal to 3 times 10, which is equal to 30. So then this is equal to the limit of f of 10 plus h, which is equal to 30 plus h minus f of 10, which is minus 30 over h as h tends to 0. And so you can again cancel out these two numbers, and of course this is supposed to be 3h, I suppose, 30 plus 3h. And so you can cancel out h and h, and so this is the limit of 3 as h tends to 0. As h tends to 0. And so that what that gives you is basically, again, you will get a 3. So what that means is that when your function is f of x is equal to 3x, then f prime of 2 was equal to 3. Also f prime of 10 was equal to the same number, 3. Now what this means is that basically we said that the derivative, if you think of this 3x as the position function for position versus time function for some stone falling down a cliff, then your stone, the position versus time of that stone is going to be this, is going to be basically this graph over here. So it would be something like this. The function goes through this point, and then this is f of x is equal to 3x. And of course then this is going to be x and y, but you know that x represents time, and you can just ignore this part of the function. Time cannot be negative. You can ignore this part, the negative parts, the negative x's. But then as you can see, if x represents time and if y represents basically the position of that stone with respect to time, as you are increasing your time, the distance of your stone from some point 0 is increasing and increasing. As you can see, this line is basically with x increasing, y is increasing. And of course, well, this is a line, f of x is equal to 3x. You know that the slope of this line, the slope is equal to m is equal to 3. At any point on this line, the slope is equal to 3, because it doesn't really matter whether you take your some point over here, for example, you take some point over here and some point over here, and for example, let's say that this is the graph of the function at this point, and let's say that this is the y-axis, for example, at this point. If, for example, if this is x is equal to 1, for example, if x is equal to 1, and here let's say that x is equal to, I don't know, probably 4, for example. Let's say that 1, 2, 3, and 4, for example. At x is equal to 4, f of 4 is equal to 3 times 4, which is equal to 12. Now, if I find the average velocity of the stone between these two points, it's going to be 12 minus, and this point over here is 3, this point over here is 12. So the average velocity would be 12 minus 4, 12 minus 3, 12 minus 3 over basically the change in time, which is 4 minus 1. So this is 9 over 3, which is equal to 3. The average velocity is 3. Now, if I get a little bit closer to this point, for example, at this point, if at x is equal to 2, f of 2 is equal to 2 times 3, which is equal to 6. So this point is 6. So again, v of average 2 is equal to basically 6 minus 3 over 2 minus 1, which is equal to 3 over 1, which is equal to 3. So of course, since this is a completely straight line, we know that the slope of a straight line at any point on the line is, or between any 2 points on the line, is going to be the same value, 3, 3, 3, and it doesn't matter which 2 points you take on the line. Since this is a straight line, the slope is not going to change. What that means is that the instantaneous velocity of this stone is basically constant. It's not changing, because the graph of the position versus time function of that stone is a straight line, and we found the same thing over here when we calculated the derivative of the function with respect to x. We saw that everywhere at any point we were getting the same value, 3, 3, 3, and so on and so forth. So that means that in the case of a stone where the position of that stone versus time is represented by a straight line, then the instantaneous velocity of that stone at any point is equal to the average velocity of that stone between any 2 points. That's basically what it means. And so that's basically why we got the derivative of the function at this point was 3, the derivative of the function at this point was 3, and so on. And you pick any other point on the graph of this function, you're going to basically have the same derivative, meaning that the instantaneous velocity of this object is not going to change, and it's going to be basically this graph over here. This is the graph of the instantaneous velocity related to f of x, which you can call it f prime of x, which is equal to 3, just a constant function. So that's basically that. But Of course, it's going to be different in the case of some object, which is basically, in physics, basically we say that if the object is accelerating or decelerating, meaning that the position of the rate of change of the position with respect to time is changing, basically, and that is represented by some function, for example, something like this. You can see that over here you will get essentially you're getting a curved line, not a straight line. Over here your instantaneous velocity at any point is changing. But when you have some straight line like this, then of course your instantaneous velocity is not changing. It's equal to the slope of the line at any point, and the slope of this line is not changing. So that's basically the whole story here. Okay, so we have a couple more examples. We will go through them one by one, but again, it's important that you understand that example of the stone. Otherwise you will not be able to understand the concept of the derivative. The concept of derivative is very tightly linked to that stone falling off the cliff, and I suppose that's basically how Newton found all of these laws about the derivative and the integral and the whole of the calculus. In the first place, he had the same problem that he wanted to basically solve, the problem of motion. And once he tried to solve the problem of motion, he came up with calculus. Otherwise, it just didn't exist in mathematics before. So that's why it's necessary to understand that situation of the stone falling off the cliff in order to understand the concept of calculus, basically. Okay, so the next example that we have is example number 6, which we want to find the derivative of the function. We have a function over here, f of x is equal to 2x squared plus 3x minus 5. We want to find the derivative of this function at x is equal to -1. You want to find f prime of -1. So we said that f prime of a is equal to the limit of f of a plus h minus f of a over h as h tends to 0. And what that means is that then f prime of -1 is, in this case, is equal to basically the limit of f of -1 plus h minus f of -1 over h as h tends to 0. Now you need to calculate these two things. First of all, you need f of -1 plus h and f of -1. So your function is your function is f of x is equal to 2x squared plus 3x minus 5, and f of negative 1 plus h is going to be equal to 2 times basically negative 1 plus h whole squared plus 3 times negative 1 plus h minus 5, which is equal to, well, you can think of this part as h minus 1 whole squared, which is equal to h squared minus 2h plus 1. So that is 2 times h squared minus 2h plus 1. Negative 3 plus 3h minus 5. And that is equal to basically 2 times h squared minus 4h plus 2 minus 3 plus 3h minus 5, which is equal to 2 times h squared negative 4h plus 3h is equal to negative h, and negative 5, you have basically negative 8 over here, plus 2 is negative 6. So that is f of minus 1 plus h. Now f of negative 1 is equal to 2 times negative 1 squared plus 3 times negative 1 minus 5, which is equal to 2 times 1 minus 3 minus 5. So this is negative 8 plus 2 is negative 6, is equal to negative 6. So f of, so then to calculate this over here, I can just keep this one. So this is basically f of negative 1 plus h. So I can write this as the limit of f of negative 1 plus h, which is 2h squared minus h minus 6 minus f of negative 1. f of negative 1 is negative 6. That the opposite of that is positive 6 plus 6 over h as h tends to 0. And what that's equal to is these two will cancel out. And so you have the limit of basically h times 2h minus 1 over h as h tends to 0. H and h cancels out. So you will have the limit of 2h minus 1 as h tends to 0, which is equal to the limit of 2h as h tends to 0 minus the limit of 1 as h tends to 0. So this becomes 0 in the limit, because as h tends to 0, then the whole limit goes to 0. You can think of this, for example, as a function. You can think of the limit of basically 2h as h tends to 0. We can write it as 2 times the limit of h as h tends to 0. And then this part over here, you can think of it as some function like, for example, y is equal to x. You can think of this as x, for example. And then y is equal to x is basically some line with slope 1, something like this. So you see, as x tends to 0 here, the value of the function is 0. So that means that the limit of h as h tends to 0 is equal to 0 simply. So then this is 2 times 0, which is equal to 0. So this part is 0. 0 minus the limit of 1 as h tends to 0, and that is equal to -1. There is a negative sign over here, and the limit of 1 as h tends to 0 is equal to 1. So that is -1. So your limit over here is -1, I suppose. So that is -1, and then the next part of this question is so what this means is that the slope of this line at the slope of this function at x is equal to -1 has to be -1, and we will see about that, how that happens. Now we want to prove that f of 0 minus f of -1, or f prime of 0 minus plus 3 times f prime of -1 is equal to 0. We want, in the case of the same function, we want to prove that basically f prime of 0 plus 3 times f prime of -1 is equal to 0. So f prime of 0 for this function is of course simple, because if you want to calculate f prime of 0, your function is basically your function is f of x is equal to 2x squared plus 3x minus 5, and f prime of 0 would be equal to the limit of basically f of 0 plus h minus f of 0 over h when h tends to 0. Now f of 0 for this f of h for this f of 0 plus h is the same thing as f of h. So f of h for this function, the limit of f of h for this function is going to be 2h squared plus 3h minus 5, and f of 0 for this function is going to be -5. So that's minus -5, which is +5 over h when h tends to 0. So these two will cancel out, and then you have the limit of basically h times 2h plus 3 over h as h tends to 0, and that is that. So then you have the limit of 2h as h tends to 0 plus the limit of 3 as h tends to 0. In the limit this becomes 0 because again this is the same thing as 2 times the limit of h as h tends to 0, and that's equal to 2 times 0 basically, which is equal to 0. So that's 0 plus basically, and the limit of 3 as h tends to 0 is equal to 3, so that's equal to 3. Now the basically over here we found that f prime of -1 was I don't remember what that was. F prime of -1, we found that to be something like it's basically that. Let's calculate it again. The limit of basically f of -1 plus h minus f of -1 over h as h tends to 0. That's the f prime of negative 1. So then you have so the function is f of x is equal to 2x squared plus 3x minus 5, and so basically f prime of f of negative 1 plus h, f of negative 1 plus h is equal to 2 times negative 1 plus h whole squared plus 3 times negative 1 plus h minus 5, which is equal to 2 times, well, h minus 1, so h squared plus 1 plus minus 2 times h plus 3 times negative 1 plus h, negative 1 plus h minus 5, which is equal to 2 times h squared plus 2 minus 4 times h minus 3 plus 3 times h minus 5, which is equal to 2 times h squared. Now this is negative h, and negative 8 plus 2 is negative 6. This is f of negative 1 plus h. And f of negative 1, f of negative 1 is equal to 2 times negative 1 squared plus 3 times negative 1 minus 5, which is equal to 2 times 1 minus 3 minus 5. That's negative 8 plus 2 is negative 6. So then that f of negative 1, f prime of negative 1 is going to be this value. Is going to be equal to the limit of basically this value. This is 2 times h squared minus h minus 6 minus f prime of negative 1, which is equal to positive 6 becomes over h as h tends to 0, and these two will cancel out. You can take this as the limit of basically h times 2h minus 1 over h as h tends to 0. Then these two cancel out, and you will have the limit of 2h minus 1, which becomes the limit of 2h minus 1 as h tends to 0, which is equal to, in the limit this becomes 0, so this is the negative 1. So the f prime of negative 1 is negative 1. So what that means is that so f prime of 0 was equal to positive 3. So f prime of 0 over here is positive 3. Positive 3 plus 3 times f prime of negative 1, 3 times 0, 3 times negative 1, 3 times negative 1 is equal to basically 3 minus 3, which is equal to 0, which is basically what we were looking for. Okay, so that is that. And there is a remark over here that says that at this stage, note that evaluating derivative at a point involves effective use of various rules limits are subjected to. The following illustrates this. Okay, so now one thing that we need to, that I wanted to do here was that we found that the oh, we had actually calculated this over here. We didn't really need to do that. So you see that basically the f prime of -1 for this function, meaning that the slope of this function at -1 was actually equal to -1. Okay. Now let's take a look at the graph of this function. Let's see what that means in terms of the graph of the function. So I draw the graph of the function over here, and I will show you once I've done that. So f of x is equal to 2x squared plus 3x minus 5, and at x is equal to -1, at x is equal to -1, as you can see. So this is x is equal to -1. At x is equal to -1, there is a tangent line that can be drawn to the basically a line tangent to the graph of the function at this point, which is effectively the slope of that line is x is equal to -1. That is basically the slope of this function at this point, at x is equal to -1. You see, the slope of the function at this point is a straight line with a slope -1, basically. Okay, so that is that. So I'm going to end this video here, and then in the next video we will continue with the rest of this discussion. I'll see you in the next video.